Hi everyone. I'm gonna be solving problem 3 today because all the other problems were already solved, and I thought this one was the most interesting because it kind of introduced something new that we didn't really go over in our virtual classrooms. The problem itself, though, we have seen before. This is a 3D pendulum, so unlike the normal pendulum that just rotates about some horizontal, about some vertical, I mean. This one also rotates about the horizontal. So now we have two angles to keep track of. So that means we're going to have two generalized coordinates for our Lagrange. So I started by defining the r vector. Now, obviously, L is, we know that the r vector is L in the ER direction, but I decided to put it all in the n frame here just so it'd be easier when I took this derivative. It kind of becomes pretty trivial. And the way I did that was just thinking about what happens when the angles kind of move around. So, we know sine of 0 is 0, and then cosine of 0 is 1. So, kind of thinking, oh, well, the phi component is off here. And if that was the case, then we know that the vector now points completely in the n1 direction, and vice versa. When the phi component is on, then we're pointing directly in the n3 direction. Then I didn't even rewrite down the velocity vector just as it was pretty trivial at this point. It's just a product rule. So like it would look like cosine phi dot cosine theta plus sine phi sine theta theta dot. Just repeating that over and over. So it just kind of becomes a lot of terms. And similarly, taking that dot product was just a lot of multiply it. Oh, wait, a trig identity exists for this. That simplifies it. Just kind of repeating that. And this was the term I ended up with because, like I mentioned, a lot of the trig identities kind of work themselves out. Then the reason I found this, the reason I found the r dot, the squared r of r dot vector was because we needed the kinetic energy for our Lagrange. So obviously that shows up here, 1/2 mv squared. And then we also need our potential energy for this system, which is just going to be the downwards component, in this case L cosine phi, mgl cosine phi, and now this is typically negative, but by definition of the Lagrange, subtraction becomes a positive. And a key observation that kind of becomes important for the rest of the problem is that there is actually no theta here, which is going to have some funny implications for our equations of motion. So then actually solving them, starting off with our theta dot, we notice that there is no theta, so we're not, this partial just goes to 0, which means we just end up with, taking the time derivative of it with respect to theta dot. Sorry, taking the derivative of theta dot, which is just this squared term over here, and we end up with this expression. And essentially, what you end up finding out is, hey, if I integrate this, we're going to have it equal to a constant. The second part of the Lagrange was a little more interesting because we did have a phi and a phi dot component in it. So I just took both of those partials and I ended up with this equation that interestingly does have theta dot in it. So, still depending on two variables for now. Then my proof for the fact that we can have an ignorable coordinate if our Lagrange does not depend on it was just saying, hey, this is the equation for Lagrange. As you can see, if it does not depend on q, it cannot have a partial with respect to q. So then we just have this derivative is equal to 0. You go ahead and solve that with integration, and it's going to just be equal to some constant that we're later going to solve for. So then going ahead and actually doing that, I said, some constant is going to be equal to dl d theta dot, and then move that over there. Go ahead and solve for theta dot. So we get this expression of some constant over ml squared sine squared phi is equal to our theta dot. Then going back, essentially all I'm doing is just plugging that back into this original equation. And what that gives us is we can then go ahead and solve for an equation for phi, the acceleration of phi, with respect to just this constant instead of having our second generalized coordinate. And kind of a quick one this time. I mean, I just thought it was an interesting idea. But the problem itself I don't think was too difficult. But, if I made any mistakes, please feel free to point that out. Thank you.